Okay, let's unpack this. Imagine gazing up at the night sky, and just a mere 4 light years away, our closest stellar neighbor, Proxima Centauri, beckons. Around it, we found a planet, Proxima Centauri b, nestled right within its star's habitable zone. On paper, this sounds like a dream, doesn't it? A prime candidate for life, practically in our cosmic backyard.
It really does capture the imagination, that proximity.
But is it truly a potential haven for alien life? Or is it, a desolate, inhospitable rock constantly bombarded by stellar fury?
That's the core question, isn't it?
That's our mission today, to dive deep into the sources you've shared, dissecting the latest scientific understanding, to give you a clearer picture of whether Proxima Centauri b could support alien life, and so what that life might look like, or perhaps where it might hide.
Indeed. What's fascinating here is that while Proxima Centauri b occupies that tantalizing Goldilocks zone where liquid water could exist, the actual conditions on its surface are, well, far from certain.
Right.
We'll be exploring the extreme challenges this world faces, challenges that might seem to rule out life entirely. But critically, we'll also examine some ingenious and surprising scenarios where habitability could, against all odds, still exist.
Which really makes you think differently.
It forces us to truly reconsider what habitable means beyond our Earth-centric view. This isn't just about looking for an exact Earth twin. It's about understanding the remarkable adaptability of life, or, the conditions that might foster it, even under the harshest cosmic pressures.
So we're going to sift through all the complexities, from the relentless barrage of intense radiation to the intriguing possibility of hidden subsurface oceans, to give you a comprehensive understanding of Proxima Centauri b. We want to arm you with the nuanced perspective on whether this planet is a viable candidate for alien life, and what the latest science suggests about its potential. Let's get started on this deep dive. Proxima Centauri b, the very name, sparks a kind of cosmic wanderlust, doesn't it? Just think about it. It's the closest exoplanet to our own solar system.
Closest, that's key.
This isn't just an interesting factoid. Its proximity makes it an unparalleled target for observation, for study, and potentially for future missions. Our sources consistently highlight that it's nestled right there in the habitable zone of its star.
Exactly.
When you hear closest exoplanet and habitable zone in the same sentence, it's almost impossible not to get genuinely excited about the possibility of finding life, perhaps even complex alien life, on such a world. That combination alone draws us in.
Yes, and this proximity is absolutely crucial. To elaborate, the habitable zone is conventionally defined as the region around a star where, given an appropriate atmospheric pressure, temperatures could allow for liquid water to exist on a planet's surface.
Right, the could is important there.
Very important. This is a fundamental starting point, because liquid water, as far as we currently understand, is the absolute prerequisite for all known forms of life. Proxima Centauri b's placement within this zone immediately elevates it to a prime candidate for potential habitability. From a distance, it suggests an Earth-like potential, which is what so often captures our imagination and fuels, well, the vast amount of scientific research dedicated to this fascinating world. It gives us a strong reason to invest resources and intellectual energy into investigating further, despite the considerable hurdles.
So, on paper, Proxima Centauri b sounds like the perfect celestial neighbor, a real contender in the search for alien life. Its closeness means we can gather much more detailed data with our current and upcoming generations of telescopes than we could for most other exoplanets, offering an unprecedented opportunity.
A unique window, really.
But the devil, as always, is in the intricate scientific details, isn't it?
Oh,
the sources make it abundantly clear that while its address is promising, the environment it finds itself in is incredibly harsh, challenging that initial optimistic outlook and forcing us to question whether its habitable label is truly deserved. Here's where the plot thickens considerably, perhaps even becomes daunting. The first and arguably most formidable hurdle for Proxima Centauri b is the sheer relentless amount of high-energy radiation it receives.
That's a major one.
Our sources vividly describe Proxima Centauri as an M-type red dwarf star, which, despite being significantly smaller and cooler than our sun, appears to be considerably more feisty and volatile. What makes these M-dwarfs so much more aggressive in terms of radiation?
That's a critical point. While M-type red dwarfs are indeed smaller, generally only about 10–50% the mass of our sun, and cooler, emitting most of their light in the infrared, they possess a peculiar and potent characteristic: intense magnetic activity.
Oh, magnetic fields.
Exactly. This activity drives frequent and powerful stellar flares, which are essentially explosive bursts of high-energy X-ray and ultraviolet UV radiation. Unlike our sun, which flares occasionally, M-dwarfs can have flares that are hundreds or even thousands of times more energetic relative to their baseline luminosity, and these events occur much more frequently.
Wow, much more often.
Much more. The data indicates that Proxima Centauri b, due to its extremely close orbital distance, just 0.05 astronomical units, or about 7.5 million kilometers, compared to Earth's 150 million, receives hundreds of times more extreme UV radiation than Earth does.
Hundreds of times.
Hundreds. To put that into perspective, imagine our sun blasting us with not just a mild sunburn, but a constant, brutal assault of the most damaging forms of radiation. It's a non-stop high-energy bombardment that would be lethal to most known surface life.
Hundreds of times more. That's an astonishing amount of energy. So if we consider a planet trying to hold on to an atmosphere, which we know is absolutely essential for liquid water and any kind of surface life, how does this continuous high-energy radiation specifically impact its ability to do so? Are we talking about simply cooking it away or something more complex?
Well, it's more than just heating. This brings us to a critical point. The continuous bombardment of such high-energy radiation has the potential to strip away a planet's atmosphere over geological timescales.
Strip it away. How?
These energetic photons, particularly the X-rays and extreme UV, can ionize atmospheric gases, essentially ripping electrons off atoms and molecules and break them down. Once ionized, these particles can be accelerated and given enough energy to escape the planet's gravitational pull into space.
So they just get blasted off the planet?
Pretty much. This process, known as atmospheric escape, can occur through several mechanisms, including thermal escape, where gases just get too hot, and non-thermal escape like ion pickup and sputtering, where the star's energy directly blasts molecules away. Without a sufficiently thick and protective atmosphere to shield the surface and maintain pressure, liquid water would be impossible to retain. It would either evaporate too quickly or freeze solid.
Making surface life really tricky.
Exactly. This makes any Earth-like surface habitability incredibly challenging, if not entirely impossible, for any alien life that might attempt to evolve there. It's like a constant planetary-scale sandblasting that effectively erodes the very air a planet breathes.
And it's not just the radiation directly, is it? Our sources also emphasize the devastating role of stellar winds. We experience solar wind here on Earth, but it sounds like Proxima Centauri's version operates on a completely different magnitude. How do these stellar winds specifically compare, and what unique threat do they pose?
You're absolutely right. It's a critical point. Stellar winds are streams of charged particles constantly emanating from the star, and they form a powerful 1-2 punch with the flares, both actively working against a planetary atmosphere.
A double whammy.
Definitely. The stellar wind impacting Proxima Centauri b may be thousands of times stronger than the solar wind that buffets Earth.
Thousands. Why so much stronger?
The why here is multifaceted. M-dwarfs, due to their intense magnetic activity, can have very strong, dense, and fast stellar winds. While Earth's robust global magnetic field largely deflects our relatively weaker solar wind, creating phenomena like auroras, Proxima Centauri b might not be so fortunate.
If it doesn't have a strong magnetic field.
Precisely. If it lacks a strong global magnetic field, or if its magnetic field is overwhelmed, these powerful winds can directly interact with and erode its atmosphere.
Thousands of times stronger. That sounds less like a breeze and more like a constant planet-shaping hurricane, a never-ending torrent of high-energy particles.
It's a good analogy.
What would that level of stellar wind do to a world's atmosphere, especially if it's already being battered by radiation and struggling to hold on? Could it completely sterilize the surface?
Such intense stellar winds could indeed easily erode a planet's atmosphere through mechanisms like ion sputtering, where high-energy particles physically knock atmospheric molecules into space, and charge exchange, which effectively weakens the atmosphere's grip.
So physically knocking bits of air off.
Yes. If the atmosphere is stripped away by this combined assault of radiation and stellar wind, the surface would become effectively barren and utterly exposed to the full, harsh vacuum of space. Surface habitability would become highly improbable, even for incredibly resilient alien life.
So even if life got started, it might just get blown away.
Essentially, yes. The key takeaway here is that these aren't just minor atmospheric leaks. They are potent forces that can, over billions of years, physically blast away the very air the planet breathes, leaving behind a cold, airless rock. This process can render a world utterly unsuitable for life on its surface, even if liquid water initially existed there.
Okay, let's unpack this next challenge, tidal locking. It's a concept that sounds really dramatic. creating a planet with a permanent day side and a permanent night side.
It is dramatic.
This has some pretty stark and profound implications for habitability, doesn't it? It's just a world of truly extreme contrasts.
It is a dramatic and often unavoidable consequence for planets orbiting so closely to their parent stars. Proxima Centauri b, being so near its star, is highly likely to be tidally locked.
Meaning one side always faces the star.
Exactly. One hemisphere of the planet would perpetually face its star, bathed in eternal daylight, while the opposite side would be plunged into perpetual frigid darkness. Think of how our moon is tidally locked to Earth, always showing us the same face.
Right.
This isn't just an astronomical quirk. It profoundly impacts a planet's climate and its potential to host life. Gravitational forces from the star create a tidal bulge on the planet, and over eons, the friction from these bulges acts like a brake, slowing the planet's rotation until one side is permanently facing the star.
And what are the specific implications of such a scenario for habitability and the potential for any alien life? We're talking about utterly extreme temperature differences that could make most of the planet uninhabitable, perhaps even collapsing the atmosphere, right?
Precisely. Without a thick circulating atmosphere and a substantial dynamic ocean to redistribute heat across the planet, the star-facing day side would become scorching hot, potentially boiling away any surface water into steam if it ever existed.
Boiling hot on one side.
And conversely, the night side would be unimaginably frigid, so cold that it could lead to what we call atmospheric collapse.
Atmospheric collapse. What's that?
In this scenario, all the atmospheric gases, nitrogen, carbon dioxide, any volatiles the planet might possess would freeze solid and precipitate onto the night side like snow, effectively removing them from circulation and leaving that part of the planet airless and completely barren.
Wow. The air just freezes and falls out.
Essentially, yes.
Yeah.
So what if tidal locking includes the possibility of turning a potentially Earth-like world into a dichotomy of an inferno and a frozen wasteland, where only a narrow terminator zone between day and night might offer any semblance of stability for surface-dwelling life? This fundamentally alters the planetary environment to one that's utterly hostile to widespread life.
And as if those present-day challenges weren't enough, our sources tell us that Proxima Centauri itself had a much more luminous and aggressive past. It's like the planet endured a really rough childhood, a cosmic hazing ritual, which could have sealed its fate for habitability billions of years ago.
It adds another layer of complexity, definitely.
What exactly was this violent youth like, and how could it have irrevocably impacted Proxima Centauri b?
This historical factor is, indeed, a significant and often overlooked hurdle. Planetary formation and early stellar evolution are violent processes. During its early life, Proxima Centauri, like many M-dwarfs, was much more luminous and emitted even more powerful radiation and stellar wind than it does today.
Even worse than now.
Oh, yes. This pre-main sequence phase, where the star is still contracting and heating up, can be incredibly energetic, lasting for tens to hundreds of millions of years. A planet like Proxima Centauri b, forming and residing in its current close orbit during this hyperactive period, would have experienced incredibly intense conditions, far beyond what we discussed for the present day.
So what would this early, more powerful star have done to a young Proxima Centauri b, potentially before any life could even get started, perhaps sterilizing it from the outset?
This early high luminosity and intense radiation could have triggered catastrophic runaway greenhouse effect.
Like Venus.
Imagine a scenario similar to Venus, but potentially on an even more extreme scale, where the planet's primordial oceans, if they ever formed, would boil away completely, turning the planet into a superheated oven, irreversibly losing its surface water.
No chance for water then.
And furthermore, the intense UV light from the young star would cause extensive atmospheric photolysis, literally light splitting, breaking down water molecules in the atmosphere into their constituent hydrogen and oxygen atoms.
Breaking the water apart.
Yes, the hydrogen, being incredibly light, would then rapidly escape into space, essentially bleeding the planet dry of its most vital ingredient for surface life.
So it could have lost all its water right at the beginning.
It raises an important question. If Proxima Centauri b lost its water and much of its atmosphere early on due to its star's violent youth, can it truly be habitable now? Or is it a desiccated, barren world, forever scarred by its past, making the evolution of alien life on its surface a near impossibility? This challenges the very notion of habitability in the present day, if the past was too destructive.
So we've laid out some pretty intense challenges, making Proxima Centauri b sound like a truly tough place to call home. Certainly not an easy environment for alien life to emerge or thrive.
It sounds pretty bleak, yeah.
But here's where the discussion gets really interesting, showing the ingenuity of scientific inquiry. Our sources don't just stop at identifying problems. They present several ingenious, scientifically plausible scenarios where Proxima Centauri b could still manage to hold on to liquid water and potentially maintain a stable climate.
Right, it's not necessarily game over.
It's a testament to the creativity of scientific thought, pushing the boundaries of what we consider habitable and where we might expect to find life.
Indeed. Despite the formidable obstacles we've discussed, which might seem insurmountable at first glance, climate simulations and theoretical models have explored potential pathways to habitability for planets like Proxima Centauri b.
Okay, so what are these pathways?
This research prompts us to significantly expand our assumptions about what makes a world livable. It forces us to think beyond an Earth-centric view of life and consider how alien life, or the conditions for it, might adapt to these very extreme and often unique planetary environments. It's about finding the cracks in the cosmic armor, the unexpected niches where life might cling on.
First up, a fascinating concept. What if the planet has a truly massive dynamic ocean? Our sources suggest such an ocean could act as a planetary thermostat, counteracting some of those extreme temperature swings from tidal locking. How exactly would a global ocean pull off such a feat?
That's the core idea behind this intriguing scenario. If Proxima Centauri b possesses a truly large, deep, and dynamic ocean, one with vigorous, planet-spanning currents, the sheer movement of this vast body of water could effectively transport immense amounts of heat from the perpetually scorching day side to the frigid, eternal night side.
Moving heat around.
Exactly. This isn't a passive process. We're talking about massive amounts of thermal energy being moved across the planet by powerful convective ocean currents. These currents could be driven by the extreme temperature differences themselves, perhaps amplified by strong atmospheric winds, creating a global circulatory system.
So instead of two brutally extreme halves, a baking hot side and a frozen wasteland, the ocean could create a more temperate band, almost like a comfortable middle ground, perhaps around the equator, where temperatures are far more stable and conducive to life.
Exactly. This continuous global circulation would help to moderate temperatures across the entire globe, preventing the day side from boiling away and warming the night side significantly. Create a much more stable and continuous habitable zone, likely concentrated around the planet's equator, where temperatures could remain within the range for liquid water.
How would that work practically, like giant currents?
The how is through powerful deep ocean currents, much like Earth's thermohaline circulation or the Gulf Stream, but scaled up to operate on a truly global scale, constantly redistributing thermal energy. This mechanism could significantly mitigate the stark dichotomous effects of tidal locking, making the planet much more amenable to supporting surface liquid water and, consequently, alien life, perhaps even complex ecosystems within its oceans.
Okay. That's one possibility. Another compelling idea involves the atmosphere itself, but not just any atmosphere. Our sources suggest a particularly thick, dense atmosphere could be the key to overcoming the challenges of tidal locking and extreme temperatures. How would such an atmospheric blanket manage to stabilize the planet's climate?
Precisely. A very dense atmosphere, specifically one containing sufficient greenhouse gases like carbon dioxide and potentially other heavy gases, could play a similar heat redistributing role to a global ocean.
A thick atmosphere instead of an ocean.
Yes. Unlike a thin atmosphere, which would easily collapse and freeze onto the night side, a super dense atmosphere would have far too much mass to freeze out completely. Its sheer density and heat capacity would allow it to efficiently absorb and transport thermal energy across the planet.
So it would effectively trap heat from the day side and then circulate it, spreading it around to keep the night side from freezing solid and the day side from boiling, ultimately creating a much more uniform and livable climate across the planet.
Yes, that's the mechanism. It would not only warm the perpetually dark night side, but also help stabilize temperatures across the planet by creating a highly efficient global heat transfer system. Think of it like a planet-sized pressure cooker, but one that distributes warmth rather than just containing heat in one spot.
But how thick are we talking?
Well, this atmosphere would need to be much thicker than Earth's, perhaps hundreds or even thousands of times denser, with surface pressures that would crush most Earth life to effectively counteract the extreme temperature differences caused by tidal locking and prevent atmospheric collapse.
Crushing pressures, but potentially habitable?
Potentially. The why is that a denser atmosphere has more mass to absorb thermal energy and transport it via strong winds and atmospheric currents, preventing it from radiating away into space too quickly on the night side. This scenario allows for the possibility of surface liquid water and potentially surface-dwelling alien life, albeit in a very different and high-pressure atmospheric environment than we are accustomed to on Earth.
This next scenario introduces a fascinating twist on the tidal locking problem: asynchronous rotation. It sounds like the planet might not be perfectly stuck in place after all, which could dramatically open up a whole new realm of possibilities for habitability and the emergence of alien life. How does asynchronous rotation work, and why might it apply to Proxima Centauri b?
This is indeed a fascinating possibility, challenging our default assumption of perfect 1.1 tidal locking for close-in planets. If Proxima Centauri b has a sufficiently high eccentricity, meaning its orbit around its star is more elliptical or oval-shaped than perfectly circular.
Not a perfect circle orbit.
Right. Then it may not settle into a perfect 1.1 spin orbit resonance where one side always faces the star. The gravitational tug-of-war from the star would vary as the planet moves closer and farther away during its orbit, creating a dynamic gravitational torque that can prevent it from locking into that simplest 1.1 state.
So rather than being permanently stuck, it could still have a day-night cycle, which we know is incredibly important for climate stability and the kind of Earth-like life we typically imagine. This would fundamentally change the picture.
Exactly. Instead, it could settle into another stable spin-orbit resonance, such as a 3.2 resonance, much like Mercury in our own solar system.
3 spins for every 2 orbits.
That's it. This means the planet would rotate 3 times for every 2 orbits around its star. This would effectively create a more dynamic climate with a regular, albeit perhaps longer, day-night cycle. Such a cycle is generally far more conducive to climate stability and broader habitability than permanent day and night.
Why is that better?
It allows for more even heating and cooling, which prevents the extreme temperature gradients and catastrophic atmospheric collapse scenarios we discussed earlier. A rotating planet offers a much more familiar and potentially benign setting for the evolution of alien life, as temperature fluctuations would be less extreme and more predictable over a cycle.
Okay, this next scenario really makes you think about alien life in a radically different way, pushing beyond our surface-centric biases. What if life isn't on the surface at all, but hidden deep beneath, shielded from all those brutal stellar threats? This feels like a game changer for how we define and search for habitability.
This raises an absolutely fundamental question. What if habitable doesn't necessarily mean surface habitability? Even if the surface of Proxima Centauri b is a frozen, radiation-blasted wasteland, our sources suggest that internal heat sources could sustain vast subsurface oceans.
Heat from inside the planet.
Yes. This internal heat could come from several mechanisms, primarily tidal forces, the relentless gravitational tug-of-war with its star, which flexes the planet's interior, generating friction and heat similar to what we see on Jupiter's moon Io. Alternatively, residual geothermal activity from the planet's formation or radioactive decay in its core could also provide sufficient heat.
So we're talking about a scenario akin to some of the icy moons in our own solar system, like Europa or Enceladus, which we've explored with our space probes. These are worlds with potentially vibrant internal environments.
Precisely. It's a concept we're becoming increasingly familiar with. On worlds like Europa around Jupiter or Enceladus around Saturn, a thick ice shell could effectively shield a subsurface ocean from the harsh surface conditions, including radiation and vacuum.
The ice acts like a shield.
Exactly. In such a scenario on Proxima Centauri b, life could indeed thrive in this liquid water environment, completely protected, perhaps drawing energy from hydrothermal vents on the ocean floor, much like some of Earth's deep-sea ecosystems.
Life without sunlight.
Potentially. What's fascinating here is the profound implication for our search methods. Life existing in such an environment would be extremely difficult to detect from Earth. We wouldn't see direct biosignatures like atmospheric gases on the surface.
How would we ever find it then?
That's the challenge. This challenges our traditional search methods for alien life, forcing us to consider that some of the most vibrant biological activity in the universe might be completely invisible to us from afar. A barren surface in this context doesn't necessarily mean a barren planet.
Our final hopeful scenario completely changes the planet's origin story, offering a way around many of those early, brutal challenges we discussed. What if Proxima Centauri b didn't even form where it is now, but arrived later? This later migration idea sounds like a clever bypass for a rough beginning.
This is a planetary migration hypothesis, a concept that has gained significant traction in exoplanet studies, with models like the NICE model for our own solar system. The idea is that Proxima Centauri b may not have formed in its current close orbit, but rather migrated inward from a colder, more distant region of the system later in its history.
Formed further out and moved in.
Potentially, yes. This means it wouldn't have been subjected to the most extreme conditions during its infancy, during the star's most hyperactive phase.
And why would that make such a fundamental difference for habitability and the chances of alien life evolving? It seems like it's all about the timing of its arrival at its current position.
The crucial aspect here is indeed timing. This migration would have happened after the star's hyperactivity period had largely subsided and settled down.
After the worst was over.
Exactly. This later migration would have allowed the planet to form in a more benign, distant environment with a larger volatile inventory, that is, a more substantial endowment of water and atmospheric gases.
It could hold on to its water and air better.
Yes. By moving into its current close orbit only after the star had settled into a more stable, albeit still active, phase, Proxima Centauri b could have avoided the initial catastrophic atmospheric stripping and the runaway greenhouse effect we discussed earlier. This scenario offers a significantly more optimistic formation story for a potentially habitable Proxima Centauri b, allowing it to retain its essential ingredients for life, including a substantial amount of water. It provides a gentler start for any nascent alien life, potentially giving it the necessary conditions to take hold and evolve.
So we've journeyed from extreme, seemingly insurmountable challenges to a surprising array of plausible solutions, making Proxima Centauri b a truly fascinating, if incredibly complex, candidate in our search for alien life.
A real puzzle.
But it seems like the ultimate question of whether Proxima Centauri b is truly habitable or ultimately barren still hangs tantalizingly in the balance. A really profound mystery waiting to be unraveled.
Indeed. Ultimately, the question depends heavily on several critical factors that we simply cannot yet observe directly. The precise presence, density, and composition of an atmosphere, the existence and depth of a substantial global ocean, and the planet's exact orbital and rotational characteristics are the absolute key unknowns.
Things we just don't know yet.
Exactly. We can run sophisticated climate simulations and speculate based on our current understanding of planet formation and stellar physics, but we desperately need hard observational data to move beyond hypothesis and definitively confirm or rule out habitability. This is truly where the cutting edge of exoplanet research lies, pushing the boundaries of what is observable.
And that's where the incredible power of future technology comes in, right? What cutting-edge tools are scientists hoping to use to pierce through the veil of light years and finally get these answers, settling once and for all whether this closest neighbor is a potential haven or a desolate desert for alien life?
That's absolutely right. Future observatories are specifically designed and being built to tackle exactly these challenges and push the boundaries of our understanding of exoplanets to an unprecedented degree. The James Webb Space Telescope, for instance, with its unparalleled infrared capabilities, is already beginning to conduct exoplanet atmospheric characterization.
Webb is looking at it.
It's capable of it, yes. It can analyze the light from the star as it passes through the planet's atmosphere during a transit, looking for specific absorption features that indicate the presence of molecules like water vapor, carbon dioxide, methane, and, crucially, potential biosignatures.
Looking for signs of life in the air.
Potentially. But even more powerful next-generation ground-based telescopes like the European Extremely Large Telescope, ELT, or the Giant Magellan Telescope, GMT, are under construction. These colossal instruments, with their massive mirrors and advanced adaptive optics, will provide even more powerful data.
Bigger telescopes on the ground.
Much bigger. They aim for direct imaging of exoplanets and spectroscopy of their atmospheres, allowing us to resolve finer details. These instruments are designed to provide the crucial data needed to determine the planet's atmospheric composition, density, and climate, which will be absolutely essential to resolve the debate over its habitability and the potential for any alien life, either confirming one of our hopeful scenarios or definitively underscoring the challenges. The prospect of finally getting these answers is genuinely thrilling. #outro.
What an incredible deep dive. From the relentless, intense radiation of its parent star and the dramatic implications of tidal locking to the intriguing possibilities of a hidden subsurface ocean or a dense protective atmosphere. Proxima Centauri b is truly a world of extremes and tantalizing complex possibilities.
Absolutely.
It's not a simple yes or no when it comes to habitability or the potential presence of alien life, but rather a rich, complex tapestry of conditions that scientists are still working diligently to unravel.
It really highlights that our understanding of habitability is far from static, and that worlds across the cosmos can be far more complex, dynamic, and surprising than we initially imagine.
Definitely not just looking for Earth 2.0.
No. The journey to understand Proxima Centauri b underscores the profound importance of looking beyond simplistic, Earth-centric definitions of life and embracing the rigorous scientific process of questioning, theorizing, designing innovative solutions, and eventually making precise observations. It challenges us to broaden our understanding of where and how life might exist in the universe, forcing us to think creatively about the myriad forms and environments life could take.
And that brings us to our final thought for you to mull over. What does it truly mean for a world to be habitable if the most exciting forms of alien life might be hidden deep beneath an icy crust, completely out of sight, potentially undetectable by our current methods?
A profound question.
Or consider how many other worlds out there, initially deemed barren and lifeless to their harsh surface conditions, might actually be teeming with life in unexpected ways in subsurface havens, under dense protective atmospheres, or even evolving in environments we can barely conceive.
The possibilities are vast.
This deep dive into Proxima Centauri b serves as a powerful reminder that the universe is full of astonishing surprises, and when it comes to the search for life, we've truly only just begun to understand our extraordinary cosmic neighborhood.